of the faces, and I'm not yet old enough for that to mean that, it's just that we're all doing symplectic topology, and I'm just don't remember, can't recognize faces anymore. But instead, I interpret it to mean that this is not an audience of experts. So instead, I should start with some giving you some setup for what it is that we're doing when we say the words Fukaya categories, and that's what I'm going to do. But I will try to do things somehow at a high level and not go into like how the soup is made, and more like about what the properties are like and how we use things. So of course, Fukaya categories are things associated to a symplectic manifold. So M is going to be our symplectic manifold. This is a smooth manifold, and omega is the differential two form, which is closed and non-degenerate. It's volume form. And the pair omega is what we call a symplectic manifold. Okay, and there's going to be some examples appearing, and when the examples appear, I will say it's a symplectic manifold, and I will try. And if I don't tell you what the symplectic form is, then you should tell me what's the symplectic form. Okay, and there's only one other notion of this type of thing that I want to define, which is what it means to be a Lagrangian submanifold. I'm not going to get much of this talk out of this talk, but it's okay. So submanifold L inside of M is a submanifold of half dimension with omega restricted to L identically 0. Okay, so omega is a two form. So what you're going to require is if you take any two plane that's contained in this tangent space of this Lagrangian, then it evaluates to 0 on it. Oh, and then I said it, but I didn't write it with dimension of over R of M times the dimension R of L. Okay, so there is something in here about the fact that omega is two-dimensional, and omega to the n is a symplectic form that tells you for some integer n. And well, that integer is, well, the volume form has to be the dimension of M, so that tells you the dimension of M is 2n. Okay, so these are the objects, and again, I'm not going to talk too much about it, but it's easy when we draw pictures. We want to draw pictures. Well, pictures are easiest in dimension 2. So, basic example: M is a Riemann surface with area form. And L is just a curve. In the sense of differential geometry. So now there is some huge machine that takes so probably the first person to suggest that such a thing should exist is Kinsevich. History is very interesting. Kaya, and then I'm going to put Ota Ono, because once it was thought that this machine to exist, so this was like early 90s. It was early 90s. Kinsevich went to Japan and gave some lectures. Fukaya was there and was like, oh, I recognize what the structure is. We can do it. Maybe order slightly different, but anyway. And then it took them like about 10 years to be able to write what this idea would be. So we can associate M. Well, if M is sufficiently nice, I'll come back to this in a second. But here I will just say, which is closed. So closed, symplectic, act, closed in the sense of, again, differential topology without boundary. So for Riemann surfaces, a closed Riemann surface. Okay. A category Let's just call it F M, and maybe I skipped something. This is some choice of ring. Okay, and this is some kind of K-linear category. That's the first thing, and then we realize that there's more structure that I should say. Okay, and then people often say, with objects given by Lagrangians, but that's not really true. But I will just say with objects given by by Lagrangians plus extra data. Okay, and the reality is that you can have a category with objects given by lots of things and still be completely uninteresting if all the morphisms are zero. In some sense here, really, more like the morphisms aren't quite defined in general, but anyway, let's do this. But what I want to say is that this category, you should think of it as living over the disk, over a disk. Okay, so this category is more like a family of categories. We're gonna have to make this more precise in a second. And this disk, the way you should think about it is that it parametrizes fact that the symplectic manifold always comes in a family. So I have the symplectic form, it satisfies this property, but I can just rescale it. Okay, parameterize the fact that we can rescale. Omega. Positive. Oh, wait, it's maybe even negative. Why not? By real numbers, and still get us. Lectic. Okay. So this is the kind of when you say gluing Fukaya categories, this is the kind of gadget we are trying to glue. Well, why would we try to glue? We really are trying to compute. Cool. Compute these categories. Okay. So again, compute categories. That sounds like a crazy thing because, what I want to point out is even if you compare, this is some kind of K-linear category, you could maybe compare this to some kind of category of modules of a ring. You compare to categories of modules over nice ring R. Okay, but that's not very plausible task because what does it mean to compute a category over some given ring? Well, it would mean, for example, one interpretation is you classify all the objects and you classify all the morphisms. Okay, well, there's one ring R for which I know how to do this. If R is let's say just a field, then I know how to do this. Then you can all objects ISO to R to the n for some n, and let's say P here, B for dimension, and morphisms are given by matrices. Great, I feel very smart. But it's very well known that as soon as you go out of this range of very, very simple algebras, then you cannot do this anymore. You can't really kind of hope to be able to write down the classification of all the modules and compute all the morphisms between them. But in the world of modules, of rings, you can still say something. Note, in this other world, by the way, the relation between this world and that world is some kind of mirror symmetry, but just for us right now, this is just some kind of what would it mean to compute? Well, this is one. Even when you can't give such a nice classification, you always know that every object, every module has a surjection from something free. I'm not going to use, I just call the module So of course, okay, maybe D is not an integer because maybe it's finite, whatever, it doesn't matter. Okay, whatever it is, everything is has a surjection from a free thing. Okay, so you can't call, you can call this, I mean, this is not an explicit computation of the category, but it tells you some kind of structure. It tells you that, in the modern language, we have to figure out how to get rid of this word surjection, but it tells you like the module, the R itself kind of generates this thing. And if you were to understand R itself really, really well, then in some abstract sense, you've understood this very well. This in some non-trivial sense. Now, why am I saying all of this? I'm saying all of this because we don't have something like this for Fukaya categories, okay? So when we say we want to compute Fukaya categories, it doesn't mean we're trying to get to this. Right? That's too hard. We're not going to be able to say these are all the objects in the Fukaya category, and these are all the morphisms between them, and these are all the compositions. It's just completely hopeless. We're trying instead to do something like this. There is some object or some collection of objects, and if we were to understand this object and the collection of objects, then abstractly up to some operations which are not very explicit, like, well, take kernels of, take co-kernels of all possible maps between frees, okay? Then in that sense, we've recovered it, okay? So we're aiming for something. Or like, okay? So now, who is the enemy? Why is this so hard? Okay. So this is hard because these categories are very well, I mean, they're hard to compute, but like, they have unexpected properties. For example, so say conjecture. So for a generic symplectic manifold, whatever that means, symplectic manifold, this Fukaya category, and K vanishes over the punctured disk. Okay, like, so okay, so I said it lives over the disk. I wasn't precise. I'm not yet going to be, I mean, not even sure I'm going to be precise today. Because we're about to do we're about to restrict ourselves to some smaller class of things. So it lives over the disk. So well, if you family of things over the disk, you can just remove zero. Now you have something over the punctured disk. What does it mean to be vanished? What does it mean for something for a category to vanish? It means like all Hom spaces vanish. Spaces are zero. Now I'm doing some, again, usual thing. This is a k-linear category, so it would have been better if I worked at the chain level, and that is what I have in mind. I have in mind that you work with the chain complexes, and in that case, I'm not saying that something is zero. I'm saying everything is acyclic, precisely acyclic. Okay, so if that's the case, we kind of, I mean, of course, you can just say, well, in that case, this is true because there's just a zero object. Everything's generated by the zero object. But somehow it tells you that we have no grasp, no ability to construct objects which are likely to be potential generators in general. Okay, we just don't know. Like these categories a priori could, if you come from algebraic geometry and this is what you have in mind, you're used to studying object categories where kind of, again, you may not be able to describe every object explicitly, but you have a handle on it. You can say, well, it may not be explicit, but whatever it is, it must be the kernel of some map like this. I mean, not this one, but the one from something free thing surjecting onto the kernel of this map. Okay, whatever that is, you have something. You can get started somewhere. Here, you get started with, well, the objects are Lagrangian, so all I have to do is list all the Lagrangians, but we don't know how to do that. We don't know how to write down all the Lagrangians in the symplectic manifold. Okay, I mean, except for Riemann surfaces. Okay, so his conjecture is not, I mean, I don't remember. Paul wrote some paper, Paul Seidel. So maybe this is known for K3 surfaces. I don't remember. I thought I should have. This is close to being known. For K3 surfaces, very delicate arguments. Arguments of Seidel. roughly speaking, what he did is he found some K3 surface. This was a long time ago for maybe first non-trivial proof of mere symmetry for Calabi-Yau's from K3 surface for which with a symplectic form for which you can actually compute everything, and everything is very nice like this, like he has a generator. Okay, and then you deform it, and by comparison, what happens on the algebraic side, you see that when you deform everything, all the objects should die. None of the objects should survive the deformation. But then you have to make sure no new objects die, no new objects are born, and there's some delicate thing that no, I'm not going to say, but it's the strategy for doing it was shown by Paul Seidel. But somehow it's just expected for, again, generic forms on tori, generic or symplectic forms, symplectic structure. Sure, on 2n torus, which I mean by the 2n torus, what you do is you linear. So here it's being presented as R2n modulo some lattice. So basically, somehow, if the lattice is rational, lattice is like Zn, let's do the simplest case. And this is very nice because somehow the lattice itself the lattice directions themselves, they collapse down to Lagrangian tori, and you can use them to generate everything. So this gives you some kind of this torus, and then this direction goes to this curve, and the other direction goes to that curve, and there's plenty more like closed Lagrangian submanifolds you can use. But if your lattice is irrational, well, this picture doesn't make sense. This picture is too easy. Somehow, it's not about rationality. It's really about like we're looking for we're looking for even dimensional things. So basically, if you in the next dimension, you may not be able to find a plane, okay, that's spanned by the Lagrangian plane that's spanned of the lattice. So if you can find planes in the lattice, you take planes that are spanned by two linearly independent directions in the lattice, but the symplectic form won't vanish on them. So when you collapse, you don't have a Lagrangian, and then this doesn't work. Okay, so this is the problem. Okay, so because this is so hard to do, yeah, that's what the theme of the lecture series is. I want to say something about how do you glue things. Well, if this is going to be helpful to glue things, first you need to be able to compute things. Okay, so that's the next thing I want to talk about. What kind of computations do we have? What are the kind of basic pieces for which it's more or less straightforward to get an actual answer? At least, well, maybe at some 20 years ago it wasn't straightforward, but by now it's more or less straightforward. Any questions before I continue? I think I have like an hour and a half to. So anyway, plenty of time to pause. So, okay, so next is kind of basic computations. Well, before I get into basic computations, what I'm going to do is we want to kind of this dependence on the disk, the parameter in the disk, it makes life very complicated. There is a special situation, special case in which the category, in some sense, is constant over the disk, that doesn't vary over the punctured disk. And that's the case in which the class as a symplectic form in the second cohomology is 0. So you can imagine what's really is going on here is that if you rescale the symplectic form, and in general, when you rescale the symplectic form, you get a genuinely different symplectic manifold, which means genuinely different means that you take m omega and then lambda omega, and genuinely different means there is no way to map this to this by a map which will take this symplectic form to the one that's being rescaled. Okay, and the obvious obstruction to these being related by a map which preserves the symplectic form is if you try to just integrate the volume form. If you try to integrate it, then on this side you will get the volume, and on this side you get the volume of m multiplied by lambda to the n. So there should be no such thing. But of course, that assumes that this quantity is finite. Okay, so this condition here, condition that zero implies that m cannot be compact. So there's a special class of symplectic manifolds which necessarily are non-compact, for which you should be able to find these things. Okay, so let me give you an example. So e.g., if m is well, this is very stupid. R2n. This is too stupid. Come back to this in a second. I need to give you some symplectic form. So the standard thing to do is to use p and q coordinates. Okay. So what this means is that, there's an Rn with p coordinates times an Rn with q coordinates, and then omega is equal to the sum of pi dq, dpi which dqi. Okay. And then I'm supposed to give you to show you that if I took lambda times omega, well, lambda times omega is just the same thing except with lambda in front. Okay, that's the sum of d lambda pi which dqi. Okay, and then it's pretty obvious what I'm supposed to do to make sure that, to get this identification, this map from M to itself. I just take R2n to R2n. Oh, it's not where I don't put it. So you just take R2n to R2n by E Q goes to lambda P Q. Okay. But once you put yourself in the situation where you can just take this scaling and just interpret it as something happening on half of the variables, you can just rescale half of the variables. Okay? So this is the prototypical case of what are called cotangent bundles.
But the lambda looks more like a real parameter here, not like
a
parameter.
Yes. I think you should imagine that, yes, you're absolutely right. So lambda is a real parameter, and this disk that I'm talking about, at least from the point of view of symplectic topology, that's the part of it that is most meaningful. And the complex direction coming from is really, there's no complex direction really. Complex direction really has to do with what ring K I picked. I haven't said what K is. If K is the complex number, then it becomes very natural to think it as a complex disk. But if K is something else, then, that's not how you should think about it. You should think of it as like some kind of K-adic, you take some ring involving K and then power series with real coefficients, and that's what's going on.
K, but the K just enters the morphisms?
The K, yeah. So in fact, the K enters in some more complicated way, but for these kind of objects, it basically only enters in the morphisms. The K enters in a more complicated way because I said there's supposed to be some extra data. This kind of data tends to be like a local system. And so then K would enter into that kind of data. Thank you for the question. Okay. And great, that gave me enough time to remember that I needed to read this part. Okay, so I said that this is some prototypical example of something that is more complicated, that is kind of, well, it's basically obtained by gluing these pieces together. Okay, just imagine that you have something where locally you have P and Q coordinates, and the P coordinates just, keep moving like this so that you can rescale them. And maybe the Q coordinates are glued together into some non-trivial topology. Okay, so that's what you do. That's so just generalization. So cotangent bundles. So this is where we see some non-trivial information coming from differential topology. So let Q be a smooth manifold. And consider P star Q cotangent bundle. So this is pairs consisting of a point, so Q and Q, and then P, which is the cotangent fiber, which is basically a covector. So I have to give you some symplectic form on this. And actually, but this is what it is in local coordinates. Literally, you just put the q's, or you put coordinates for this thing, and then the p's are like the dual coordinates. But there is some kind of nice way to say this, which makes life a little bit easier, which is to notice that omega equals d theta, where theta is sum of pi dqi. Okay, and then you can try to think like, what is this form here? What is it for pi? And this is kind of important because it's essentially necessary to be able to do. You can prove kind of by the Cartan calculus that if there were this symplectomorphism, this transformation that takes omega to lambda omega, whatever, smooth, very smoothly in lambda, then you have to have a form which is of this type, which is what's called exact. Anyway, and then in this case, it's very easy. So I'm going to just draw. So I have to give you a one form, which means I have to give you something so that if you give me a vector, I give you a number. U is down here. I take some tangent vector v over there, and I want to produce a number, but this tangent vector, it's like based somewhere. Okay, so there's a point, little q, and a point p where this is based, and you take this tangent vector and you project to the base. So this is projection of v, so let's call this projection pi lower star of v. So pi is the projection map from t star q to q. And then you just pair v against pi lower star of v. Okay, and this is it becomes kind of very simple formula. Tautological, most importantly. Okay, and the reason that this definition is convenient is then you don't have to check any change of coordinates; it just follows. So now we know from this we have ample supply of symplectic manifold which satisfy this exactness property. And there's some more technical point that's required, but I won't really get into it. And what's this dilation to some sense? You see this was some dilation. It's exactly the same as here. Okay? The few coordinates you can't dilate because they wrap up to some, again, non-trivial topology. Can't do anything there. But the p coordinates you can just rescale them. Okay? So this is again exact. Well, it's exact, but also has this rescaling property. Okay, so now you'd like to compute this thing, and it's a little bit surprising at first. The answer, it turns out later I will say a few words about how to get an answer that's somehow less surprising, but the answer is that this is zero. This category is again zero. Even this one was zero in the sense over the punctured disk. Unless Q is closed. Okay. But what I want to do is that now that we have this rescaling, this tells us that all the fibers away from zero are the same. So we define the exact Fukaya category. Fukaya category to be fiber of the actual Fukaya category. F of M over the 0.1 in the punctured disk, or in fact any point because they're all isomorphic. Any non-zero point. And this is kind of for every ring K, you can just produce a K-linear category like that. Okay, now we're going to describe it. And again, this description feels like something is missing, and I'll try to say something in the end of it. What's missing? Theorem. F. Okay, but let's call it exact. Okay, let's just let me just give it a name. So I'm going to put here exact. Okay. T star Q K vanishes unless Q is closed, in which case it is equivalent to the category of derived local system. Of derived local systems. And now I have to say one modifier, since finally making something that is called theorem, okay, which So they have need some smallness properties. So usually in Fukaya categories, I talked about modules over a ring, and I was not being precise, but when we do Fukaya categories, things have to be basically finitely countable. This. I'm just going to say with some finiteness properties. And then I'll explain. Just because in symplectic topology, it's very hard for us to produce very large rings. Okay, so let me now explain what I mean by that. So these, what do I mean by derived local system? Well, I mean something like you have, I think we understand what the local systems are. So i.e. Vector space, well, K module. Oh, okay, so now there's this word derived, okay. So I'm gonna say chain complex. Let's use the word Q of K modules for every Q in Q plus, okay, so K, that's a fairly natural thing. That would be like a local system of K module plus parallel transport maps. FQ to FQ prime, which are chain maps for every path. Okay. And if we wanted actual local system of chain complexes, then we would just say, well, and then whenever you have 3 paths like this, you can concatenate. Okay. And yeah, so then you would like to say they agree. Sorry, they concatenate. Well, concatenate, that's actually true. When they have 3 homotopic paths, I take it back to that. So it takes 3, say 2 paths, the concatenation of 2 of them is homotopic to the third, then you would say, well, these 2 things should give me equal maps. But instead, what you have is a homotopy. Homotopy of chain maps. For every homotopy paths. So this sounds like some crazy amount of data. But actually, it's not so bad.
Your definition also for the case of cotangent bundle of exact category?
No, I said this exact category somehow makes sense whenever you can rescale. And then I said,
what happens to the fiber when the M is closed?
So when M is closed, you cannot make sense out of this because then it will depend extremely strongly on which fiber you pick.
Yeah, that's why I don't understand the definition.
So what I said is the exact Fukaya category to do the fiber at any point, because then I don't have to specify what the point is. They're all the same. In the exact case, there's scaling.
Definition for Liouville manifold making.
So yes, this is
I see.
this is the definition for a symplectic manifold where you have some rescaling, so that the symplectic.
For sure.
I see. Okay, thank you.
Okay. So anyway, for every homotopy of. Okay, so this sounds like intractable in general, but it turns out that these categories can actually be described as categories of modules, or not quite over a ring, but over a differential graded algebra. So let me just explain the first non-trivial case, and that would be the case where where Q, with this cotangent bundle, is the circle. Well, where Q is closed manifold is a circle, and M is its cotangent bundle. Yep. You want me to lift this board up?
No, the underneath.
Other one. You want this one to be sent out. Maybe too strong. Okay.
Maybe can you say
Yes.
what happens if you just take the category of local systems on a non-compact?
Okay, so to get it,
Have any symplectic interpretation?
yes, it absolutely has a symplectic interpretation. So this has to do with the fact that with how you, it's much better to say this for something with boundary. If you have a symplectic manifold with if you have if Q has boundary, then what you can do, and I will say this in a second, is you can define some category associated not to the symplectic manifold T star Q by itself, but to the pair T star Q and T star of the boundary of Q. This sits as some kind of symplectic submanifold sitting inside the boundary of T star Q. Okay, and then the Fukaya category for this pair is more closely related to what you want. This will not be zero. I stated something just because, if you just follow the definition, you can say this is exactly what manifold. You have to do a little bit of change, but this would be the most naive thing. Like 10 years ago, this would have been what would have been the natural answer. And now we can define this object, and we're like, yeah, this is better. Okay. Yes. Okay. So Q is S1. And then, I don't know. That's T star S1. M is equal to T star S1. But we're talking about local systems, so that means that somehow you have some data at some point here and some other data at some point here. But you see, there's no room for homotopy because everything is one-dimensional. You take this path and then this other path, and there's no two homotopy. But what's only interesting thing is you can go the whole way around. Okay? So in this case, you don't really need the full strength of these derived local system. You can get away with a little bit less. So the derived local system on S1 is essentially the same as a K module. Oh, I see. I'm supposed to erase that. I'm sorry. Plus an invertible endomorphism. Why do we need an invertible? Where is the invertible endomorphism coming from? The invertible endomorphism is coming by going around the loop. Okay, and it has to be invertible because if I go around this way and then I go around this way, then that should basically be the identity because I can retract that loop. So this is therefore a T inverse module. Okay. But this is actually some object that we could have described explicitly in terms of Q, which is that we could just take the homology of the base loop space of Q. The base loop space of the circle. So let me just say this. Base loop space. You take the homology of the base loop space. That's a ring. In this case, the base loop space of the circle is just consists of, it has like one component for every number of times that you wind around. This base loop space has a composition map. So we have this kind of loop Q times loop Q going to loop Q. Which will just, okay, so this starts with some loop based here and some other loop based here, and you put them together, and they're based on the same point to make our life easier. Same base point. So maybe I should write something here. Chosen base point. Right, so maybe this is the base point. And there's really not much more data. Take a point, and at that we just have to remember all monodromies are for all loops going through that point, and that up to Morita equivalence, whatever, will determine the category. So that's the answer for S1. But in general, looking at the homology was the wrong thing to do. In general, the correct thing to do is to start with the structure at the level of spaces, and realize that it defines a map at the level of chains. That makes it look very much like this object has a multiplication, and this is what I said, this is a differential gradient. And this can be quite interesting. For example, so there was this, question. Okay, so in the case of S1, there is this monodromy which is going around S1, but in the case of S2, there's also some kind of monodromy. So this is Q equals S2. S2 is confusing because it's both a symplectic manifold and is, can be used as the basis of cotangent bundle. But here I just mean like we're looking at M equals T star S2. I can't draw M equals T star S2. I can write an equation for it, but come back to that later. Okay, and then we pick some base point here, Q. And this is simply connected. Okay. So, well, the loop space of Q. Let me just say S2 here. This is just the ground ring. Okay, so looks like we're not going to see anything, but H1 is non-zero. Also, basically. And it's basically coming from the fact that there's this one parameter family. Okay. So I start with a constant loop, and then I draw one parameter family of loops, and then when I come back, I'm back at the constant loop. That's non-trivial. But you can tell it's non-trivial because basically if you choose an extra point and you evaluate, you get the degree 1 map. The degree 1 map from, you cover every point on the circle so that you cannot retract this to a point. Now, the reason I'm saying this is because now you can do very interesting things, like you can take S3 over S2, which is the Hopf map. Okay. And, at every point you have a circle. Okay. So then you look at the homology of the fiber. That's this F. At every point you take the homology of the fiber. And then you'd like to say, well, there's clearly no monodromy because again, pi 1 is 0. Okay. But there is higher monodromy in this sense. So this kind of contains a lot of non-trivial information. So these are the things we can compute. And, again, you can say this is this computation. Well, it's a reduction to something else, but it's a reduction to something where you now have like a grasp on things. Okay? It's not, as I said at the beginning, if somebody just hands you a symplectic manifold, you just don't know what to do. You don't know how to produce any interesting Lagrangians. But when somebody says something like this, then they're like, oh, well, there's interesting objects. There's a trivial module. Maybe there's some other module. Maybe there's like, oh, I just said it's modules over some DGA. Well, this DGA itself will define, will be a generator in the sense of, earlier I said everybody will have a surjection. That's not a technical term, but that's basically what it is. Okay. So that's the first class. And I just want to say, it's very important for the purpose of mirror symmetry that this example here generalizes. Okay, so KTT inverse module, this is basically just the category for mirror symmetry. The case where Q is S1 times S1, let's say n times, and torus is some kind of like 0th order thing that we have to understand, and it works out very well. Gives that the Fukaya category again exact of T star of torus is the same as some kind of modules. I'm not going to be precise enough here to just say over the ring K. Okay, so T1. That's a really horrible use of this T's. Normally we use X's or Z's, but anyway, plus or minus T2 plus or minus. Okay, Tn plus or minus. Okay, by the same logic, somehow the universal cover of the thing here is contractible, so there's no interesting topology in the base loop space like there was in the case S2. Instead, all there is just loops and concatenation. And now this you can understand as some kind of coherent sheaves, coherent sheaves maybe. But again, I'm not being precise enough with what kind of modules. Over what do people write? GN. So when K is C, this is like C star to the N. But it's basically like take a function plane and take an N full power. Okay. So this computation, which can be accessed in many ways, in some sense, the easiest way to access it is by thinking about the generality of cotangent bundles. Okay. So that was one thing we can compute. And then I want to talk about another example we can compute to give us something kind of non-trivial to get our hands on. So this is, I mean, just,
I'm sorry.
yeah, this.
Why, I feel I said something, but no, like, why do you have this half?
I wanted to give an example of some interesting module, some interesting derived local system that kind of, goes beyond just an ordinary local system where the monodromy is just going around one loop and getting, a matrix. Okay. And so what I'm saying is that the first example that I know of something where the word derived becomes very important, okay, is the example of the hop map. If you take the hop map S3 over S2,
Right.
the fiber is a circle. Then you can take the homology of the fiber. That's just that's just two. This is the homology of S1. It's just two things. K, direct sum K shifted by 1. Hopefully, yeah. Okay. So if you look at each of them separately, there's no interesting monodromy because if you were to go around the loop, you would have a transformation of this K itself, but every loop is contractible. And so the transformation of the identity. But if you go around this family of loops, then you will get a transformation, which in fact takes this piece to this piece. Because you have something that's non-trivial of degree 1 in the ring, I mean, -1, that's okay. And that's somehow the sense. That's why the word derived local system has non-trivial content. Another way to say this is, if you take the constant loop, okay, you should be, by the formalism, you should be getting the identity map. Now I have a 1-parameter family of loops that are homotopic to the constant loop. So what I should get is a homotopy from the identity to itself. And that homotopy can be non-trivial.
So your Q is S3.
No, Q is S2.
Two.
No, Q is S2, and I know it's slightly confusing. The base is S2. And I'm producing a local system over S2 using the topology of the Hopf map. Q is S2. Okay. So at every point in S2, so a local system means at every point in my base, I have some K module. Okay, so my K module is the homology of the fiber of the Hopf map, the circle. And I go from fiber to fiber. I can just connect them because there's no critical point. I just follow the homology. Homology doesn't care. Okay, great. Thank you. Okay. So yeah, just some. So more complicated. So that's 3 more complicated examples, just so that you can have some flavor. So these are coming from again mirror symmetry, but really kind of gross Siebert study of toroidal degenerations. So now I'm going to write some formula. So far, every time, yeah, we've only done cotangent bundles. I've given you what the symplectic form is. So I'm going to look at C to the n plus 1. Okay, so C is basically R times R. Okay, but maybe we use X and Y. Okay, and then we use the symplectic form, omega equals dx by dy. But when I write the complex numbers, that's what I mean. Cross C star to the m. Well, C star is just C minus 0. So that's great. So these guys I will give coordinate Z, and these I will give coordinate W. And inside of this, I'm going to write some interesting to me, maybe not to you, symplectic manifold. I'll call it X, M comma N. And it's given by an equation, some Zi equals 1 plus product of Ci. sum j equals 1 to m of yj. Not called y, w. Some equation. Okay. And okay, so this is a symplectic manifold. How is it a symplectic manifold? It's a symplectic manifold because this is a symplectic manifold. Okay? And you can just restrict omega from en plus 1 plus c star to this to xm. Now, you can't just restrict things willy-nilly without because you need it to set, it's always going to be closed. That's not the problem. But you need it to remain non-degenerate. But this is actually quite simple because omega is actually a Kähler form and X is a complex manifold. So automatically this will be non-degenerate. Kähler. So we're pretty happy. What's a little bit takes quite a bit more work is to actually understand that this has this kind of dilation property. I'm not going to get into that. So this also is of the class of things for which the exact Fukaya category makes sense. Okay. Again, if it's an affine hypersurface, we can just do it. Okay, so now we have some theorem that says the exact Fukaya category of XMN is equivalent to some kind of coherent sheaves on derived category of coherent sheaves on X and M. Okay. So that's slightly surprising. So all I did is I switched the variables here. This derived category of coherent sheaves, you shouldn't worry about it because it literally is modules over some ring, let's see, R, which is like I take K and I put ZIs and I put the WJs and I put plus or minus 1 and I mod out by the defining equation. Let's just call this little f mn. So we're back to the case of just rings over modules over a ring. Okay, so this takes a long time to prove, and I'm not going to go into the details, but I just want to point out some basic things. So this very large class of examples, very large, whatever. Fairly large class of examples. But let me just explain a little bit of the geometry. And let's do the first case. If the case is too degenerate, then not so interesting. I want to do x11. By the way, it is kind of shocking statement because you see here, the Fukaya category takes the ring as input. Just take the Fukaya category of this symplectic manifold, some object that's constructed out of complex thing, and it tells you, well, if you take this symplectic thing and you feed it some ring, like the p-adic numbers, whatever, some ring, or z, even better, the integers, then you'll get modules over this ring where now k is z. Okay, so if seen talks where mirror symmetry is some kind of duality between complex Calabi-Yau manifold, which is the correct context of it, this is kind of strange because now we're computing things where k is not the complex numbers, and we're getting out of some object of differential topology, some object of pure algebra. Okay, and probably the philosophy is that these objects are so well defined, that so kind of canonical, that they're like defined over the field with one element, but I don't know what that is, so you don't worry about it. Okay, we just observe that we have this choice of k, and it gives us a lot of different. Okay, so what I'm going to do, I'm going to set n m equals 1, 1, and try to understand what this is. So this is some hypersurface inside P2 plus C star W, given by the equation x 1 x2 equals 1 plus W. Okay, plus Z. This is Z1, Z2. Well, that's not very interesting because W is just determined by Z1 and Z2. And we can just entirely get rid of this variable here. Okay. But let's point out one thing, W is not allowed to be 0. So this is the same thing as the subset of C star squared given by pairs Z1, Z2, such that Z1 times Z2 is not equal to, okay, you can just work out 1. Okay. So, yes, yeah,
I'm late, so I didn't know.
yes.
Like,
Please ask your question without apology. Yes.
like, I thought Fukaya category is the about and the object is symplectic manifold or symplectic object and morphism and Lagrangian correspondence.
So,
then that's
not quite. Not quite. The Fukaya category is something that takes symplectic manifolds to F is something that takes symplectic manifolds to categories. Okay. So now the objects here are Lagrangians. So the objects of F of M are not exactly, but should be thought of as L inside of M, which is Lagrangian submanifold. And now, just because unfortunately, I'm a mathematician, I have to tell the truth and say with extra data. Sub manifold with extra data. But for practical purposes here, okay. So I haven't talked at all about any of these Lagrangians. So that's why I said we're just treating things formally, and I'm just telling you there's a computation. Computation tells you it's the same as local systems. And the reason that I'm doing it like this is that, if we spent our time talking about Lagrangians, then, well, this would have to be 3 lectures of 80 minutes each, not 2. But so I'm saying let's just treat it as a black box. With cotangent bundles, we just get this answer. This answer is very interesting. It allows us to do a computation that otherwise would be inaccessible. And I wanted to give one more example, which is this class of examples here, where I'm not going to tell you about what the Lagrangians are. I'm just going to tell you, somebody proved that there is an equivalence between this Fukaya category and categories of modules of this ring over some ring. Okay. And now let's see what it tells us. Let's just see what it gives us in examples. Okay.
Can I just ask?
Yes.
So this category of modules over this ring is very big. Does that tell us that we have a lot of Lagrangian submanifolds or a lot of extra data that we can?
No. This tells you basically there are, well, haha, very good. In some ways, so this category of modules of this ring is generated by one thing, which is the ring itself. Okay. So the most important thing is to find that ring itself. Now, if you have some very interesting module, it's going to be very tricky to point out the actual Lagrangian that corresponds to it. And, then it depends like how much are you willing to stretch the extra data that you're going to put in this Lagrangian. In some sense, you can make it tautological. The extra data is you take the Lagrangian, which is going to correspond to the ring itself, and then you just put on that Lagrangian a presentation of this module. Okay, that's kind of, not very interesting. So there's a tension here between making the object as geometric as possible. Again, I'm not saying much about because I'm not saying much, and making the correspondence between this side and this side, as explicit as possible.
Thank you.
Thank you. Any other questions? Somebody else? Okay, so there's this. So this is very interesting. So this is just a subset. Remember, we already said that like if I take Rn, R2n, I get 0. But if I just remove this thing from R2n, then suddenly I get something non-zero. Not only something non-zero, but actually something interesting, which is the same thing. So the statement in this case, we get the Fukaya category of, and I will just write it here explicitly. Well, I'm going to do it like this. Z1, Z2 not equal to 1 inside C2. Coefficient in K is equivalent to modules over, well, I said the same thing. This is hilarious thing. This is n plus m, so nothing changes. Modules over the ring, which is A, Z1, Z2, modulo maybe I should call them W1, W2, but it's too late now. But I mean, I'll do it with W here. Let's do it in some way. Z1, Z2, and then 1 over 1 Z2 plus 1. Okay, you just invert this polynomial because you don't allow the thing to be 0. Okay. So now, next thing that I want to say, I'm starting to run out of time, is once you see some things like this, you'd like to say like, great, now, if we're going to glue things, these are going to be our base computations, like things that we think we can compute, cotangent bundles, things like this. And the basic point is that, cotangent bundles generalize to some theory of like, Weinstein manifolds, and there is a whole machine for trying to understand them using some kind of Handel decompositions, Handel attachment. This thing you should think of as prototypical of the kind of methods that, even though we didn't use Seidel, this was not done using Seidel, that Seidel introduced, where you use like methods of algebraic geometry to take some object which is presented as a hypersurface or maybe complete intersection in some nice enough space, and then use some complex algebraic geometry techniques to study its Fukaya category. So these are our starting boxes, and now we want to relate them to each other, but to relate them to each other, we need some functors. So there's very, very general perspective here that's due to Verheim Woodward. Which is that functors from the Fukaya category of M1 to the Fukaya category of M2 are induced by Lagrangians living inside the Fukaya category of the product. So this philosophy is somehow extremely important. This is the kind of point of view where, if you look at the citations, you look at the papers, like not many papers actually kind of use this point of view explicitly, but philosophically it's important and it's why things work. So how would you do that? Well, let's just, schematically, if I take some, schematically the object of the Fukaya category of M1 are just Lagrangians in M1, okay? So you take L inside M1, let's call it M1. And then you take M1 cross M2 here, and you take L1, 2. There's a projection map. And what you want to do is you want to somehow push this L1 to M2 by pulling back and project. So define composition to be fiber product. So you take L1, it maps to M1, you take L1, 2, it projects to L1. You take the fiber product, pairs of points here and here, which have the same image. You can project down here, but that's not going to be so interesting. Then you can project down to, but the interesting thing is to move back to M2. Okay? Or more precisely, projection of this. Projected. It takes some work to, it takes a little bit of work to show that this will preserve the Lagrangian property, but it takes an enormous amount of work to say that this is compatible with the kind of structure that underlies the definition of the Fukaya category. But that's how we think of it. But what I want to talk about is much simpler, toy case. What if M1 is just a subset of M2? Well, if M1 is a subset of M2, there's very, very nice Lagrangian that's contained in M1 times M2. Okay, there's a small trick having to do with you have to switch some symplectic form, but let me just do this. Let me write it like this. So you can just take M1 itself, but included by x goes to x comma x. The picture I have in mind is, so this is my M2, and maybe I could do this in M1. Actually, that's not what I want. I want the other one. Okay. I want M2. All right, just give me 1 second. Yeah, this is M2 and this is M1. That's correct.
Very well. What's that? No, you wanted the graph of the map, right?
I wanted the graph of the map. Well, what I wrote is correct.
No, and 2 doesn't.
Step back, you wrote M1 including M2.
Ah.
That's fine.
Okay. Let's hope that I didn't mess it up.
Oh.
Thank you.
You just
That
re-
was the mistake.
You just rewrote the same step.
Thank you. Okay, good. I think this is correct. That's right.
No, no, it's not.
Yeah. So,
It's okay, everybody.
oh, they got
knows
flipped
what-
around. They got flipped around again.
Hey.
Okay, what am I planning to do? Okay, M1 is an M2. I need to go from the Fukaya category of M1. The way I set it up is I want to go from the Fukaya category of M1 to the Fukaya category of M2. So let's correct everything. So this is going to be M1. This is going to be M2. Okay, now we are happy. Finally, we're happy. Great. So, so we have this, and so it's not clear that this is Lagrangian, because you have some symplectic form here and symplectic form here. So this is Lagrangian for omega on M1 and minus omega restricted to M2. This is on M1, and this is reverse the form. And the reason it's Lagrangian is because when you pull back, you're going to get omega and then minus omega, so it will cancel and you'll get 0. So now what does this do in practice? I have to stop in 3 minutes, right? Right. 5? Now yeah, maybe start a tiny little bit late. Okay. So
It says on the schedule you have until 1:45.
okay, then I thought it was an hour and a half. So it's okay. All right.
We started at 9:15.
We started in.
Ah, yes, great. Thank you. Okay, good. Then I will not rush as much. Okay, so what does this do? So now I take some Lagrangian L1 inside M1. Yes, M1, the bigger thing. And I take this fiber product. But there's not much of a fiber product to take because M2 is just a subset. Okay? Then the fiber product is just the intersection. This is the simplest possible, well, one of the simplest possible things you could do. You could just intersect. Okay, so we have a theorem that says, okay, so unfortunately there's some technical conditions, even though, okay, so
What is L1?
yeah. L12 is exactly M2. So let's check dimensions. Okay, so L12 should be a Lagrangian and this times this should be half the dimension of half of the sum of the dimension of M1 and the dimension of M2. But in this case, they're equal dimensional. So L12 should have just the dimension of one of them, and I just pick the smaller one. Okay. I mean, I can't pick the bigger one because the bigger one doesn't fit. Okay, so on a, I'm going to say here, nice. Let me actually say something more precise with it. Category of Lagrangians in M1, Lagrangian 1, with the property that L M1 intersected with the boundary of M2 mapping into L1 intersected with M1 minus M2. That's horrible. Interior of M2. Being a homotopy equivalence. Okay, just treat this as a technical box. On this subcategory, this procedure, this intersection procedure, defines a functor from to the Fukaya category to the exact Fukaya category of M2. And this thing needs a name. I'm just going to call it exact M1, and I'm just going to call them nice. Okay, kind of a strange statement. But what it says is that there's some technical condition. The technical condition, I'll just draw it and tell you what the enemy is, and then we can just move on. So I said that what you don't want to happen is for there to be non-trivial topology. Oh, great, I even have a picture. You don't want for there to be non-trivial topology outside. So for example, like this would be quite bad. One is not nice. Why is it not nice? Well, I said I take L1 intersected with the boundary of M2, that's these 2 points. And I said that this included inside L1 intersected the complement is homotopy equivalence, but it's not in this case because you go around and these 2 points which were disconnected become connected. So what's required for it to be nice? This would be nice. Okay. This one's good. So this kind of functor, it's called Viterbo restriction functor. And it was essentially our first tool for defining functors on Fukaya categories. Now, in order for that to be useful, you need to be able to produce such inclusions that are nice enough, where the Fukaya categories are not going to be 0. Well, this is actually one of them. I didn't, I'm not going to quite do it explicitly, but this was used by Heather Lee to compute Fukaya categories of punctured Riemann surfaces. Maybe I should say again the exact Fukaya categories. Punctured Riemann surfaces. How did she do it? Just draw. So you take some punctured Riemann surface. It takes a bit of work to set everything up correctly, but at the end of the day, what you will do is you'll basically cover it by pairs of pants and have intersections between these pairs of pants given by cylinders. Sorry. I have to decide exactly how to draw this picture, but let me just draw it like this. I'm going to give myself some room. Okay, so this is There's color. Great. Okay, so here's a pair of pens. Okay. And well, that's going to make us closed here. So let's just do that. And then here maybe some other pair of pants. Let's go somewhere else. Sorry, this is not behaving very nicely. I should have prepared this part better. See, what I'm trying to avoid is things that glue back to themselves. But maybe I don't need that. Let me just have things that glue back to themselves. I'm not worrying about it too much. Okay, so I'm going to cut this like this. So there's some kind of pair of pants that's kind of overlaps like that and goes like this. There we go. That will be acceptable for the purpose of this talk. Okay, so there's some pair of pants and some other overlaps here. And on the overlap, this is not exactly how she did it. There is the cylinder. And then in the next part, for example, I could have another pair of pants, do something like that, and then those. So now, if I could just compute and compute Fukaya categories of pairs of pants and the Fukaya categories of cylinders, okay? And well, cylinder sits inside a pair of pants in multiple ways, but it sits, for example, here at the end. And that's an inclusion. Cylinder inside there. So then I get out of this surface, I get some kind of diagram. Of categories that I can compute. And her answer, her theorem is that out of this diagram of Fukaya categories, which are just pairs of pants and cylinders, you can obtain the Fukaya category of the surface as an appropriate limit. Okay, so Fukaya category of the surface somehow should have restriction maps to all of these. And that's the first time that we can kind of start using these the tools, the kind of computational tools of this nature, to kind of bootstrap from basic examples to more complicated. Okay, so tomorrow, the main thing that I will talk about is some formalism for everything here, and I apologize, I stopped writing it. Oh, here, I still write exact. Everything here was in the world of exact things. Okay, so tomorrow, we will talk about, doing something like this, or defining version of these restriction functor, turbo restriction, in the non-exact setting, without exactness. And we'll encounter much more complicated situation, and it's not going to be anymore the case that we can formulate the functor as a Fukaya category of a symplectic manifold to the Fukaya category of the submanifold. Instead, we're going to have some setting where we're going to have what are called Fukaya categories with support. So it's going to have a single symplectic manifold, and we're going to have compact subsets. And for every compact subset, there is the Fukaya category with support on that compact subset. That's going to be the target of the restriction functor. And then there's going to be a separate question, which is this thing with support equivalent to the Fukaya category of the thing on which it is supported? So it feels very strange from the point of view of algebraic geometry, but that's what we encounter. What I did want to say is that, and I alluded to it when Tony asked me about manifolds with boundary, that there is an alternate, approach to computing Fukaya categories in terms of diagrams that came after this work of Heather Lee, and that's been actually very, very useful. That's due to Ganachar, Partner, and Chende. And their way of doing things involves kind of more complicated gluing, more complicated, kind of introducing more objects. So let's call this addendum, so that you have the correct context for what I'm saying. So Ganachar, Partner, and Chende, but this will not show up tomorrow, so pardon. Chende introduced more general class. So a notion, let's do it like this, of Fukaya categories for pairs. So actually, this appeared earlier in the work of Sylvan. Let's see, kind of bootstrapped it into some more elaborate machine. So pairs like pairs M, and let me just call M prime. And here M prime sits inside the boundary of M. So this is called stumps. Now it's very, it'll take me a while to kind of set up the whole theory. So instead, what I'm going to do, I'm going to do instead, I'm going to tell you kind of what happens in basic cases. For example, if M is the disk, okay, now I need to have some submanifold. This is some kind of codec, let's say like a symplectic hypersurface. So codimension 2 symplectic. So now I need to choose something in the boundary of the disk that's codimension 2. Let's just point. I could choose 1 point. I'm not going to get anything interesting. I could choose 2 points. Okay. Now I'm going to get something interesting. So this category, so now you have some category like this. Let's call it that. Right? And this is the category of K modules. If K is our ground, right? Now goes back to the question like, okay, if it's the category of K module, that means that every object you should be able to identify something in here. And well, but I'm going to cheat. I'm going to tell you K modules means I just have to tell you where the generator goes. And the generator basically goes to this Lagrangian here. So the reason I wanted to say this is because, this description, which I kind of slightly botched, but it's okay. You can fix it. Involves taking some open symplectic manifold, like this open punctured Riemann surface, and taking an open cover of it. This description instead allows you to access Riemann surfaces by kind of gluing together. So if you do something like this, you can then take 2 copies of this. Here's one, and here's the other. Okay. And now there is some formalism where we can go from the Fukaya category of M prime to the Fukaya category of the stumps. So we get, this thing is functorial. You have f of M prime goes to f of this pair, f of M prime. Now I told you there's this philosophy, which I still haven't erased, this philosophy, that every functor in Fukaya category, this is not, somehow maybe still not true, but I don't know. It should be true that every functor in Fukaya categories is induced by some Lagrangian. So here I have to tell you what is there's some Lagrangian that lives inside M prime cross M, and that's again is just M prime itself. But really you have to cross it with something, cross it with R. Okay, and the picture is easiest to see in the case of a point. So this is a point, okay, and associated to this point is a Lagrangian in the whole thing. So that's actually this. You just cross it with R and you push it off a little bit. So there are two functors in this case from the Fukaya category of a point, which is also K modules. There's two functors to the Fukaya category of this interesting disk. Okay. And now I have these two functors. Okay, but it's very easy. These two functors are both just, K modules goes to itself by the identity. There's not, everything is rigid. There's not enough structure here for something interesting to appear. Something interesting will appear in the next step. I have these two things. I have the point here. This goes here and this goes here, and this point, and this goes there, and this goes there. All I'm trying to say here is, the point includes there, the point includes there. Okay, and so that induces something on Fukaya categories. K modules goes to K modules, goes to K modules, and again. Okay, and then you can try to take some kind of colimit in this case of this diagram. And this is interesting. So geometrically, if you were to just glue this together, now I really do have to stop. If you glue this together, you will get some object that we have seen before. So glue. And what you get is, well, I mean, it's okay. I mean, I don't know if I can draw. Let me draw it like this. How about this? Okay, there you go. I just deformed my shape a little bit. And then I do this one. And we just glue at these points. And you get this. Okay. Oh, this is basically T stars one. So now we have another. You see, when I started to talk, my basic pieces were, cotangent bundles because those were the ones where we check and compute. But from this formalism, you can actually go to even smaller basic pieces, which are somehow much simpler. And then glue them together and then recover the previous pieces. So anyway, so there's this. This is this Ganasha partnership formalism. Again, I will not use it tomorrow, but my point was simply that, if we have some picture here that's like, you take Riemann surfaces, you decompose them by nice open covers, you can glue categories together. Another thing you could do is you could take somehow Riemann surfaces and glue at the boundary. Okay, and this tells you can't quite do the naive thing. The naive thing would be to say, oh, you have some boundary and some other boundary, okay, and you just literally glue them together. That's not right. Instead, what you do is you have a boundary, another boundary, and then a point, and then you just glue there. Okay, just glue along that point. Put a little band. That's what I did here. Little band connecting these points. And that is the thing that actually behaves well for this, for these stop Fukaya categories. Okay, now I will stop. Thank you.
Questions?
Yeah, so I have like a basic